Okay, so Module 5 begins with Chapter 3 on chemical reactions. So this might be quite familiar to many of you. For others, it may not be, but that's okay. We'll go through it all the same, and we'll make sure that everyone is on the same level. So, and for those that know it, it's a refresher. For those that it's new to, welcome to this topic. So we'll be talking about things like stoichiometry, we'll be talking about balancing equations, we'll be talking about solubility, things like that. So in chapter 3, there are 9 major topic areas. There's an introduction to chemical equations and what they are. There are balancing chemical equations, because sometimes whenever we start off with a reaction, say between carbon and oxygen, and so we need to correct for that, and that's balancing our equation. Introduction to the chemical equilibrium. So we'll talk about this briefly, but chemical equilibrium will be discussed in detail in Chem 2. Aqueous solutions, precipitation reactions, acids and bases. Again, this is I describe them using words. Where, for example, if we're reacting methane, all right. Recording. All right. So as I was saying, methane reacts with oxygen to yield carbon dioxide and water. So the methane here is the fuel often coming from the air, and then we end up with carbon dioxide and water. And so that's a nice word description. It doesn't really tell us anything about the numbers of atoms and molecules involved. And so typically in chemistry, we'll use what's called a symbolic representation of a chemical reaction, which is shown down below. So here we have the methane, which is the CH4. And it's going to react with 2 molecules of oxygen. That's what this 2 stands for. It means that in this reaction, we're using 2 oxygen molecules. So it's 2 O2s. And then this will give us or yield carbon dioxide, CO2, plus 2 waters. So the 2 again here indicates that we have 2 waters produced. For every carbon dioxide that is produced in this reaction, 2 water molecules will be produced. That's what 2 means here. And so we have special words for the different sides of this arrow. That on the left-hand side is typically called the reactants or starting products. And those on the right are called the products of the reaction. So yeah, so we can imagine that maybe there's like a coefficient here of 1 in front of the methane and in front of the CO2, it could be a 1, but that's not really necessary. So we can also include in this the states of matter for each of our reactants and products. So in the case of methane and oxygen, at room temperature, we'll assume that it's room temperature, those are gases. Methane is very small, so it's got a high, a low boiling point. Same with oxygen, both of these are gases at room temperature. Carbon dioxide is also a gas at room temperature, but water is a liquid. So we're going to get some sort of liquid vapor, or we're going to get liquid water forming. And so our letters, just for a reminder, S is a solid, L is a liquid, G is a gas, and AQ is aqueous. This means that it is dissolved in water and it's aqueous. We'll talk about like how something can dissolve in water and other solvents. Maybe not today, but certainly next time at the very least, at the very latest. Chemical equations. So chemical equations show the reactants and products in a reaction. The relative amounts in a reaction are also shown. So for example, 4 aluminiums plus 3 oxygens give 2 aluminium oxides. And so the numbers in front here, this 4, this 3, so the 4, the 3, and the 2, these are called the stoichiometric coefficients. And they tell us about the number of molecules in or atoms involved in the reaction. So for this one, we have 4 aluminium atoms, which happen to be solids, reacting with 3 molecules of oxygen, and that's in the gas phase, to give us 2 particles of this compound, aluminium oxide, so 2 ionic compounds, Al2O3. So even though there are 2 aluminiums and 3 oxygens, this is classified as one product, this aluminium oxide, but there are going to be 2 of those. And these stoichiometric coefficients lead us to what is called a balanced equation. So what that means is that the number of aluminiums on both sides of this arrow are going to be the same. So here we have 4 aluminium atoms, and here we have 2 times 2 is 4 aluminiums in this aluminium oxide. We can do the same with oxygen. So 3 times 2 means we have 6 oxygens on the left-hand side, or the starting product side. And this then should match the number which are in the product. So 2 times 3 is 6. So we have 6 oxygens in our products, and that means that we match this side and this side. So that's what the stoichiometric coefficients are there for. They're there to make sure that we have the same number of atoms on both sides of our equation, both in our reactants and in our products. And that is to make sure that we are not creating or destroying matter. Now, the forms of that matter can be different as they are here, but it should match up the number of atoms involved. So yeah, so this goes down to the law of the conservation of matter. So because the same number of atoms are present in a reaction at the beginning and at the end, the amount of matter in a system does not change. So here we have mercury oxide reacting to give 2 atoms of mercury plus an oxygen molecule. So if we have 2 times 1 is 2 mercury, so we have 2 mercuries here, and 2 times 1 is 2 oxygens in our reactants, which means we'll have 1 oxygen molecule in our products. And so this reaction can be done simply by heating some mercury oxide in a test tube, and that will then yield mercury and oxygen. So yeah, we kind of create or destroy atoms. So since matter is conserved in a chemical reaction, the chemical equation must be balanced for mass. In other words, there must be some number of atoms, or it must be the same number of atoms of each kind on both sides of the equation. So in our previous example, we had the same number of aluminiums on the left-hand side and on the right-hand side. And for our mercury oxide reaction, we had the same number of mercury atoms on the react we did on the product side. And so this discovery is credited to Lavoisier, who discovered it some time ago. So balancing equations. So once is written, the symbolic representation, the subscripts of the reactants and products cannot be. Their oxygen is always O2. It's never. So once we write it down, we cannot change those or atoms or ions. We cannot change the form of them. To satisfy the law of conservation of mass, coefficients are used to balance the equation. So for example, in our methane reacting with oxygen, we have a coefficient here of 2, and carbon dioxide reacting, or to give carbon dioxide and 2 waters. So what this means is that for every methane molecule that we burn for energy, say, we need to have 2 oxygen molecules. And then this will produce, as a product, 1 carbon dioxide. And for every carbon dioxide that is formed, we will form 2 waters. So generally, we match stoichiometric coefficients so that everything has a whole number. There are also a few rules to follow, which we'll talk about in detail now. So here are the steps in balancing a chemical reaction using coefficients. So we write the equation using the formulas of the reactants and products and include the physical state, so the solid, liquid, gas, aqueous, etc. So the etc. just kind of means those that are sort of a little are dissolved in some form of solvent. Balance the compound with the most elements in the formula first, so we should only be using whole numbers. We don't want a quarter of this molecule reacting with 2/3 of another. We want everything to be in terms of integers, whole numbers, because usually we can't really have half of a molecule. We have the whole molecule or nothing. Balance the elements on their own last. So for example, oxygen in our previous example would be an element, and so that would be balanced last. Check, so here would be like, for example, O2. O2 is an element, so that would be the last thing to be balanced. Balance the compound with the most elements in the formula using integers as coefficients. So using, like, for example, 2 or whatever. We don't use half usually. So don't use that. Check to see that the sum of each individual elements are equal on each side of the equation. So we've already done a little bit of that whenever we looked at the aluminium oxide, we looked at the mercury oxide. We determined that, in fact, we could say that there were the same number of aluminiums and oxygens on both sides of the equation. So by doing that, we can say that we are on the road to having a balanced chemical reaction. And if the coefficients can be simplified by dividing through with a whole number, do so. But remember, we want to remain with an integer at all times. So trial and error, it's usually faster for simple equations than more systematic approaches. So in the case of our methane, reacting with oxygen to give carbon dioxide and water. And you can do that by trial and error, just sort of like figure out which numbers, because it's a very simple system. But with larger, more complicated systems, it may not be as easy or as appropriate. So chemical equations are chemists' shorthand to describe a reaction. So it contains all reactants, all products, the state of and any conditions used in the reaction. So here we have a reaction of calcium carbonate reacting to give, being heated up. So if we heat up some calcium carbonate, we will form calcium oxide, and we will also form carbon dioxide. And so we can see this is actually already a balanced equation because we have 1 calcium here, 1 carbon here, and 3 oxygens. And on our product side, we have 1 calcium, 1, 2, 3 oxygens, and 1 carbon. So we have actually a balanced equation straight off here. And this little delta, as I've mentioned in previous sessions, indicates that we have some heat being used to affect the reaction. So being heated up, this is calcium carbonate to decompose, and two leaves us behind some calcium oxide, balancing chemical equations. So each side of the equation must have the same number and type of atoms. So it all must add up. It must need to give calcium oxide and carbon dioxide, and we have a balanced equation there. We have the same number of atoms on both sides. Reactants and products both have one calcium, both have one carbon, and both have 3 oxygens. So the 3 oxygens are here, or 1 plus 3, or 1 plus 2 is 3, gives us there. Okay, so how might we go about balancing this equation? So we have ethane, the C2H6, reacting with oxygen, give carbon dioxide and water. So it is a little bit similar to the methyl we looked at earlier. So as it says here, the elemental oxygen, this O2 molecule, that will be balanced last because it is an element. So we'll balance around the other elements first. So we'll look at trying to balance the hydrogens first from our ethane. So we have 6 hydrogens on the left-hand side. So we will need to have 6 hydrogens on the right-hand side, at least initially. So there are no hydrogens in our carbon dioxide, but there are 2 in our water. So if we put a stoichiometric coefficient of 3 here, then we'll end up with the same number of hydrogens on our product side as we do on our reactant side. However, this gives us a new problem. So if we look closely at our reaction, we have here an even number of oxygens on our product side, or sorry, our reactant side always, because the only source of oxygen is from our oxygen molecules, and those are always O2. So we can only increase in multiples of 2. So we can go 2, 4, 6, 8. We cannot go 2, 3, 4, 5, 6. Because every time we add an oxygen, we're going up in increments of 2. But if we have a 3 here for our water, that will give us 3 oxygens here plus 2. That's 5 oxygens. That's an odd number of oxygen atoms. We cannot achieve balance in that situation where we have a 3 here for our oxygens. For our waters, which means that this number must be an even number, which means we're going to need to change the number of ethanes. So we'll need to have 2 waters. So we have 2. So that's a little bit easier because every time we add a carbon dioxide, we need to add another oxygen. But that's okay because there are 2 oxygens in it. So for every carbon dioxide we add, we can just add another oxygen if it is ever necessary. So what happens here is that we have 4 carbon dioxides because we have 4 carbons on our reactant side. So 2 times 2 is 4 carbons. So that means we'll need 4 carbons on this side. There are no carbons from water. So the only source of carbon on our product side is the carbon dioxide. So 4 times 1 is 4 carbons. So that's now balanced on this side. It's balanced around the ethane. So the only thing now that we need to balance is our oxygens. So what we do is we count up the number of oxygens on our product side. So we have 4 times 2 is 8, plus 6 times 1 is 6. So 8 plus 6 gives us 14. So how many oxygens do we think we need? Answers in the chat, please. If we need 14 oxygens, how many oxygen molecules will we need? All right, so far so good. So we have 4 times 2 is 8 oxygens here. Here gives us a total of 14 oxygens needed. How many oxygen molecules, bearing in mind that each molecules will we need in our balanced equation to give us 14 oxygen atoms? So that one, so we got a few more. what stage we're at. No, okay. Well, 8 times 8, so okay, 14 divided by 2 is oxygen molecule. So there's our 7. So if you already knew, so some of you told me that in the chat, which is great. Others, maybe you already knew that. That was great. So if not, hopefully you can see now where it's coming from. Just look through it, look over it. If you have any problems, just let me know. So then we can count up the number, sorry, of atoms on both sides. We have 4 carbons on both sides. So there's 4 here, 2 times 2 is 4. On this side, 4 times 1 is 2, or sorry, is 4. So it's 4 carbons on both sides. The hydrogens, we have 2 times 6 is 12. So 12 hydrogens on our reactant side. We have 6 times 2 is 12 hydrogens on our product side. And then oxygens, we have 7 times 2 is 14 oxygens on our reactant side. And here we have 4 times 2 is 8, plus 6 is 14 oxygens on our product side. And so everything matches up really well, and we're very, very pleased. Okay. So what we did there was we balanced our ethane, we balanced this equation. So we had 2 ethanes plus 7 oxygens gives us 4 carbon dioxides plus 6 waters. So what was happening there was it was not balanced in any way. We had 2 carbons on our reactant side and 1 carbon on our product side. We had an incorrect number, or sorry, an unbalanced number of hydrogens, and we had an unbalanced number of oxygens. So what we did was we balanced around the biggest molecule first, which was C2H6. So we figured out how many carbons we needed on our product side to match the 2 from our ethane. Then we determined how many hydrogens we needed in our water to balance the number on ethane. So we had 6 hydrogens from our ethane, our C2H6. And so that meant that we needed 3 waters, at least initially. So that was balanced okay. And then the next problem was, though, that we had the wrong number of oxygens. So we had a balance of carbons, we had a balance of hydrogens, but we did not have a balance of oxygens. The problem was that we had an odd number of oxygens on our product side, which was not achievable on our reactant side. So what we did was we tried to balance for oxygen. We could have put a 3.5, but as we've talked about in the rules, we always want to have an integer or a whole number of molecules. It's not really possible to have a half of a molecule. So that 3.5 would in fact give us balanced equation. We would have 2 carbons on both sides, 6 hydrogens on both sides, 7 oxygens on both sides. But since we don't have a whole number here, we can correct for that by just simply multiplying the whole thing by 2. So you can't have 3.5 oxygens. So what we do is we double the equation. So the balanced equation then will be 2 ethanes plus 7 oxygens gives us 4 carbon dioxides plus 6 waters. So that's just another way of doing it. It's doing it maybe in fewer steps, less back and forward than what we had seen. So, but it does involve multiplying all of the coefficients, and so it can be, you just really choose the method which works for you. Only coefficients can be changed. So only like the 3.5 oxygens going to 7 oxygens, oxygen molecule. That's the kind of thing that we can change. We cannot change O2 into O3 or O4, just equations. So for example, mercury plus O2, we cannot make this a mercury O2 down here. That's not allowed. Cannot do that. So what we instead have is balance like this. So we kind of just put it to there, that's that lab. So the 2 goes where I've drawn it, and there, and that's how we balance. Here we have a bunch of practice equations, which I won't go through here and now, but I encourage you to try and do it as good practice for the long tests or for the quizzes and final exam. So here we have, I'll just talk about the first one. So we have aluminium and bromine reacting to give aluminum bromide here. So we have a solid in the aluminium reacting with the liquid in the bromine to give another solid here. So the first thing we will do is we'll balance around the thing that has the most, which is this. So to go on the, in order to get this product, we'll need 2 aluminiums. So we put 2 in front of our aluminium here. And then to get 6 bromines, we'll put 3. And then we actually have a balanced equation. So this is a straightforward example. But you always start this number of molecules first, and then you balance elemental ones. Both of our starting elemental, you can just choose it. And then the others can be worked through. So I guess I could do this one at the bottom as well. So here we have iron oxide. So iron oxide, we start off with looking at the number of atoms on both sides. We've got 1 iron on this side and 2 oxygens. On this side, we've got 2 irons and 3 oxygens. So we have an odd number of oxygens on this side and an even number of oxygens on the starting material side. So our materials means that we're going to have to at least multiply this side by 2, but we'll do that later. We'll balance around this first. So our iron, there's 2 irons, so that means we'd need 2 irons here. And then 3 oxygens, so that means we would need 1.5, 1.5 oxygens. The problem is we can't have 1.5 oxygens. So we'll multiply through by 2 on everything. So that goes to 4. And then this goes to 3. Oh, why doesn't it want to work? Oh, there we go. 3, and then this goes to 2. Like that. And that's how we balance that equation. And then I'll leave the one in the middle for you, the copper oxide reacting with ammonia to give copper, nitrogen, and water. So chemical equilibrium then. So most of these reactions are actually in some way reversible. Now, a lot of them may seem irreversible, but given the right conditions and the right set of reactants and things, most reactions can be reversed. So in the case of a chemical equilibrium, when we write the chemical equilibrium, we use what's called a double arrow to indicate that the reactant can go from the products back to the reactant. So we can go reactant products, and then products could go back to reactants. Usually we choose conditions which are going to give us mostly products, but some chemical reactions can go back to the reactants. A prototypical example is nitrogen reacting with hydrogen to give ammonia. So this is the Born-Haber reaction. This is incredibly important actually to life as we know it, because this forms ammonia, and ammonia might not seem like it, but it is one of the most important molecules because it's used as a starting material for fertilizers, which are very important to make sure that there's enough food for everyone. So is an equilibrium. So depending on the temperature and pressure, we get more or less of our product. You'll talk significantly about that in Gen Chem 2. We'll just briefly touch on what an equilibrium is right now. So some reactions can also occur in reverse. So for example, ammonia going to nitrogen plus hydrogen. Under these conditions, the reaction can be written as so. So 3 hydrogens gives us ammonia. And so this is this double arrow. So it's usually actually written more like something like, why is this not working? Ooh. Something like this. So the arrow is more like more like 2 half arrows really than 2 actual full arrows. In the ones that you get in the quiz and stuff, it'll look like this. So these double arrows indicate equilibrium. So here is an example of a reversible reaction. This is going back to, or not, sorry, not going back to, this is calcium chloride reacting with sodium hydrogen carbonate to give a reaction, to give calcium carbonate as a precipitate, and CO2 gas is bubbled off. So we have here our solution of calcium chloride, and we have here our solution sodium hydrogen. So in this reaction, what we'll do is we'll mix these together. So we'll pour this one into this one, and we'll see that immediately a white solution is formed, and that's because of a precipitate or a suspension of solid calcium carbonate is formed immediately in our test tube. So water, a precipitate of calcium carbonate, and CO2 are our products. So we start off with calcium chloride plus sodium hydrogen carbonate. Which is this. Then those give us, actually it's a reaction. So to use my double R, calcium carbonate plus CO2 plus water. This is not balanced, by the way, at least not yet. Or is it? No, it's not. Okay, so that's our overall reaction. But what we see here is we have two solutions, one of calcium chloride and one of sodium hydrogen carbonate. They are mixed together, and then the forward reaction gives us calcium carbonate, which is a solid precipitate. So that's why it goes cloudy white. And then we see this bubbling, and that bubbling is because carbon dioxide gas is also produced, which evaporates from the liquid and bubbles off. Somewhat similar to opening like a soft drink or something. You see the bubbling of the carbon dioxide out of the liquid. So this reaction, as I've drawn here with the arrows, is reversible. So simply by bubbling CO2 gas back into this, we can dissolve calcium carbonate. So here we have calcium carbonate plus CO2 plus water. We also have our sodium and our chloride ions, but those are what are called spectator ions, and they don't actually do anything in the reaction. So what's going to happen here is that we bubble carbon dioxide from our carbon dioxide tank. And this is bubbled into our calcium suspension. And so those carbon dioxide will react with the calcium carbonate to give calcium ions that are dissolved and hydrogen carbonate ions. So the hydrogen carbonate and the calcium ions can then be dissolved in water. And we'll eventually go from this cloudy white through to cloudy, finally to clear or colorless solution. So if CO2 gas is bubbled into a suspension of calcium carbonate, the reverse reaction occurs. That is, solid calcium carbonate and gaseous CO2 react to produce calcium ions and hydrogen carbonate ions in solution, both of which are going to be soluble compared to the calcium carbonate that we started with here. So what is an electrolyte solution versus a non-electrolyte solution? So an electrolyte solution is something that conducts current and conducts electricity to some extent. So a strong electrolyte is 100% ions. So it means it completely separates in solution. So ionic compounds are made of cations and anions, if we recall. And so those are going to separate completely into the cation and anion in solution if they are very strong electrolytes. It means that they're going to be pretty good at conducting electricity so long as the concentration is high enough. A weak electrolyte, so more molecules than ions. So that means that they don't really dissociate so much, or the concentration is very low. And non-electrolytes do not conduct. So for example, this is if we dissolve sugar in water, that's a solution, but it's not an electrolyte solution because sugar is a molecule and it doesn't conduct electricity. So water is a non-electrolyte, more or less. The concentration of H plus and OH minus are too low to conduct. They're very, very low in concentration. They do conduct a little bit, but it's almost negligible. Mostly water molecules, yeah, that's true. For pure water, it's mostly just water. And why are electrolytes important? Well, they're important biologically because in our bodily fluids, we need to maintain a balance between the different ions and molecules in our blood and our blood plasma and what have you, in order to maintain a good bodily health. So whenever they do a chem screen of our blood, they usually analyze for sodium, potassium, chloride, phosphate, and calcium to make sure that we have a good balance of those, a good concentration of those in our blood, because if we have an imbalance, it can indicate other problems, maybe in our diet or otherwise. So usually, like with sodium and potassium, you need to have a good balance between those. So you can't have one in ascendancy, like too much sodium could, over a period of many years, lead to chronic heart problems. Potassium, too much of that can lead to some certain medical conditions. But generally, I mean, our body's really good at self-regulating. So if we have like a pretty good balanced diet, we'll be fine. Calcium or chloride, phosphate, and calcium are important for like bone structure and cellular structure. I don't actually know what chloride is particularly useful for. I know it's useful, but I'm not quite sure why. I'm not a medical person. Conductivity apparatus. So demonstrates conductivity properties. Bright color or bright light, good conductor. Specifically, like this is where we have our beaker filled with our electrolyte solution. So like salt in water, high concentration. We put 2 electrodes in there to see if an electrical current can pass through our solution. And then there's a bulb attached to it. So if the bulb lights up brightly, then we'll end up with, or we could say we have a good conductor. If it doesn't really light up at all, we would say we have a poor conductor. But we'll see an example of that shortly. Dim light, not so good conductor. No light, very poor or non-conductor. Conductivity depends on concentration. So high ion concentration is a better conductor. Low ion concentration is a poorer conductor. This kind of makes sense because if you think about it, the ion, so if we have water, we've already said that water doesn't really conduct electricity. So what is the thing which is transporting the electricity through the solution? It's going to be the ions. So the more ions we have, the easier it's going to be to transport the electricity or the current. So if we don't have a lot of ions, it's going to be harder for the solution to transport the current. Kind of just makes a little bit of sense. No, few ions, we have a weak electrolyte, and lots of ions, we have a strong electrolyte. So conductivity properties, solutions questions to ask yourself. Is it molecular ionic? So for example, are we mixing sugar into our water or are we mixing salt? Is it conducting? So one thing that we can do is we could like link it up to an electrical circuit and see if a light bulb is going to be lit up. Is it a strong, weak, or non-electrolyte? Well, that could be told to us via the intensity of the light. What is the best symbolic representation of that system? So how would we like create a schematic? So this is what I'm talking about, the conductivity demo. So here we have a beaker filled with some sort of salt solution. In this case, it's copper chloride. That's why it's slightly blue. In solution, we have, as we've seen before with our dipole interactions and our ion dipole interactions, we have the water molecules orientating themselves around the ions. So in the case of the copper 2+, we see that the negative part of the water molecules, the part on the oxygen, is pointed towards the calcium ion. And in the case of the chloride, the hydrogen atoms of the water molecule are pointed towards the chloride because those are the delta regions of that molecule. And so those orientate themselves towards the chloride. Now, this happens in solution. And so this is how the current is transported between these two black lines, or the electrodes. So one will be the electrode and one will be the negative electrode. And then those are linked up to some electrical wiring, and that electrical wiring flows through this bulb. This is a tungsten filament bulb, most likely. So it works as a kind of a resistor. It's an old-fashioned bulb where the amount of current that flows through leads to a brighter light. So this case is a strong electrolyte. You can see that it's a very bright light. It's got this white glow to it. Sodium chloride, the solution is going to be a strong, weak, or non-electrolyte. So what do we think? Do we think it's going to be a strong, a weak, or a non-electrolyte? Sodium chloride is our common table salt. Dissociating in water, or is it going to partially dissociate? So completely dissociate, partially dissociate, or not dissociate at all. So separate totally, a little bit, or not at all. Sodium chloride, our table salt. Yep. So everyone so far, yep, very good. All right. So good stuff to be a strong electrolyte. Assuming the concentration is high. We're not told that, but we'll assume it is. So it's going to be a strong electrolyte. The solute is molecular or ionic. Well, I already kind of told you that. It's going to be ionic because it is sodium chloride. This is the solute, the sodium chloride. It's dissolved in the solvent, which is in lower concentration than the solvent. So the best representation is going to be this: sodium plus chloride minus, both aqueous because they're both dissolved in water. So sugar here, sucrose, C12H22O11. Is this going to be a strong, weak, or non-electrolyte, A, B, or C? Is it going to be strong, weak, or non-electrolyte? So if in the case with our bulb setup before, are we going to see any light? Basically? And if we are, what kind of intensity is it going to be? I don't know. I'll let a few more people answer. All right. Okay. So usually we would assume that in this case, it's going to be a non-electrolyte, in fact, because the sucrose is a molecule and it's not going to dissociate at all. So that means it's not really going to be able to conduct electricity. It's not really going to be able to pass the current through solution. And so we're not really going to see any light at all. Assuming we have pure water, if like we have tap water or something, there are enough ions in the tap water that there could be a sufficient current flow. So we need to use distilled water or pure water, but you can buy distilled water from the store pretty easily. So if you wanted to do this, it wouldn't be that hard. The solute is molecular. Sucrose does not dissociate, so it's not ionic. And then the best symbolic representation would be just this aqueous. There we go. HCl, so hydrogen chloride, this is like a precursor to hydrochloric acid. Is this solution is going to be strong, weak, or non-electrolyte? So you could have a go at this. Let's see. Might know, you might not. So far, so good. Okay, this one's a little bit trickier. It is. Okay, so this in this instance, it's actually a strong electrolyte. HCl is a precursor to hydrochloric acid, so it will actually dissociate in water to form H plus Cl minus. It's a strong acid, hydrochloric acid. I haven't really talked in so much detail about this. I go into it a bit more than what we do here in the synchronous sessions. Generally, like HCl will complete. It is a strong acid. We haven't quite covered acids and bases yet. Briefly cover them in module 5, but there's topics in Gen Chem 2 about this. So it's going to be a strong electrolyte. The solute is in fact ionic. It almost completely dissociates. No, it does completely dissociate in water. It is a very strong acid. I can't go into too much detail because the best symbolic then is going to be H plus aqueous. Plus Cl minus aqueous. So yeah. Sodium hydroxide is a little bit similar to L, only this time it's a very strong base. So is it going to be a strong, a weak, or a non-electrolyte? Sodium hydroxide, like lye, you might see in the grocery store. Used as a drain cleaner, also used in making traditional soaps. Yep, so far so good. All right, yeah. After I explained the first one, it's a bit easier now, which is good. These are the sort of things that you could get in like quizzes and stuff. You know, like identifying if something is a strong or a weak electrolyte. Like not a ton of questions like this, but you would get a couple maybe. Might not get them in the final exams though. It's a bit too straightforward. Okay, yeah. So everyone that answered got it right. So it's, in this case, we have sodium plus plus OH minus. So that's some recall back to our whenever we learned about different ions and stuff way back in module 3 or module 2. I can't quite remember. Module 2, I think. So this solution is going to be strong. The solute is ionic because it dissociates into 2 different ions. And then the best symbolic representation would be Na plus aqueous plus OH minus aqueous. And yeah, we'll leave it here for today.